Here, I don't want to extend it for you because I know that you've got other things to do too, and other meetings to go to, other legislations to tend to. I appreciate so much those of you that have come, to all the members who have come, but I appreciate also members of the energy industry who've come here today to provide a presentation on this. This is something I wanted to, been thinking about doing. Our extern down here, Amid, and I've been talking about it for some time, but this session is going at such a quick pace and so many things going on that I hadn't done this. But I know the grid, and I don't, what I know about it is what I've read, what's been presented in committee. Went to an interesting meeting at NCSL when I was in Atlanta this past summer, and some interesting and, nothing against the industry people we have here, but some alarming issues were brought up about the grid and possibilities, vulnerabilities. But then on the other hand, I know that there's a lot of opportunity for improving the grid, and we want to hear about that, of course, and increasing the intelligence of the grid, and everything that everything that relates to it as far as safety, national security, people being able to perform their daily duties, and the economy and everything like that. So thank you so much for coming today. Before we go into that, though, there is something else important. I should have turned this on. My grandson, who is paging today, is calling me, so I'm sorry. I never tell people. I never ask you to turn your phones off because I think that this is a grandson here, but I think that when the phones ring, a lot of times it has to do with commerce and doing our jobs and feeding your families and meetings that facilitate deals and things like that. So I never ask people to turn their phone off. And I didn't, but I should have put it in my pocket or something so I could have. But before we do that, before we talk about the grid, first of all, I would just like to recognize Chairman Geisinger. And Chairman Geisinger and I got together last week to talk about Representative Dudgeon's bill, and for Chairman Geisinger to kind of look at who he wanted on that subcommittee to look at that bill over the summer. And so, Chairman Geisinger, if you would announce. You don't have the list. Okay. That's okay. We sent the list out. Everybody who's on that subcommittee has received an email notifying them that they're on the subcommittee. But what the goal is, and what I know Chairman Geisinger is going to do is take this bill. The session will be over a week from tomorrow, I guess it is, if everything continues to go the way it's scheduled. No, I'm sure it is. And between then and the time the session starts next year, to get together and have some meetings and talk, of course, with the author of the bill and those who have input, and come back with a report to us at the beginning of the session next year. Chairman Geisinger.
I wanted to point out that we will not have any meetings until after the 20th May, which happens to be primary day.
That's a good idea, Mr.
The small print. It's Representative Holmes, Representative Dickey, Representative Hamilton, Representative Ben Harbin, Representative Smith, and Representative Drenner, and myself are the members. There's 7 of us. No. Thank you.
Thank you. And with that, we will get into this presentation. Would recognize John DeAndrea with Georgia Power.
Thank you, Mr. Chairman, members of the committee. Hope you're having a good afternoon. I'm John DeAndrea, the Legislative Affairs Manager for Georgia Power Company. And speaking for all the electric utilities that are here today, we appreciate this opportunity to come and participate in this joint presentation about a very important topic, which is obviously the electric grid in Georgia. We're very fortunate and, quite frankly, very proud of the grid that we have here in the state. All the companies represented here today work very hard and use really a set of foundational principles that guide our planning, operations, maintenance, and security of our electric system. And those guiding principles are to provide our customers with the safest, most reliable, and most affordable product possible. And those are kind of the guiding principles we use as we plan, maintain, and operate our grid. And I think by keeping the citizens of Georgia at the forefront allows us to hopefully make the best decisions for our companies as well as for the state of Georgia. Let me take just a few minutes and outline what we'll do here for you today, and I'll direct you to the screen over there. The first slide I'm throwing up really just is a very simple diagram. Some people, and when we talk about the grid, some people take the idea that it's from the generator on the far left side all the way to the home or business on the far right side. And technically that is exactly what it is, but the true backbone of the electric grid is the transmission system. And when I talk about transmission system, on the right side, the third thing from the left, it says substation. If you can think in terms of everything back from the substation back to that generator on the left-hand side is what we term the transmission system or the bulk power supply system. People talk about it in different terms. And I like to think about it and make things simple. If you think about the transmission system, think of it in terms of the interstate highway system that we have. So the transmission system is a lot like the interstate highway. It's high speed, it's high volume, and it's an interconnected network to deliver power to the substation.
Sir, I'm going to interrupt you just for a second.
Absolutely.
I apologize. Sir, could you identify who you are and who you're with?
I'm Jim Walls.
And who are you with?
I have a website called Atlanta Unfiltered.
Okay, thank you.
But again, we think of to simplify it, the transmission system is kind of like the interstate highway system. If you think of from the substation to the right in the distribution system, it's more like the surface streets. Those are designed to basically carry the product to that end user or the ultimate place that we need it to end up. Both are critical components, the transmission and the distribution end of the business, but they both perform different functions. Today's presentation, we're primarily going to focus on, Mr. Chairman, the bulk transmission side of the system. And at the end of the presentation, we'll have an opportunity, hopefully, for a Q&A type panel, and we'll be glad to answer any questions you have, regardless transmission, distribution, or otherwise. Before I turn the presentation over to Russ Schuler from Georgia Transmission, I'd like to point out that in your packets, we've provided you with a couple of documents. One is really a synopsis or some talking points, if you will, and one is a Wall Street Journal article. Last Friday on the 7th of March, the Federal Energy Regulatory Commission issued an order, and they issued that order to the North American Electric Reliability Corporation, or you'll hear it referred to as NERC, to act within 90 days to develop standards that will require utilities to take steps or to demonstrate that the utilities have already taken steps to address physical security risks and vulnerabilities related to the reliable operation of the bulk power system. So that partnership between the federal regulatory agencies and the industry, a lot of the things we'll talk about today have already been addressed. I believe the utilities that are here today, we already have plans both from a physical security standpoint and other standpoints to protect the grid. Let me leave you with one comment. There's nothing more important in our business than be able to provide our product to customers in once again, a safe, reliable, and affordable way. So we take the security of the grid very seriously, and we take the partnership that we have with our federal regulators that regulate the grid system very seriously. So I'm going to sit down, but it's my pleasure to introduce Russ Schuler from Georgia Transmission. He's going to take you through the major part of the presentation.
Thank you. Thank you very much, Mr. Chairman and committee members. We're very honored and grateful to be able to come here and talk about our transmission system. Before I start, I say our transmission system. The transmission system belongs to Georgia Transmission, Georgia Power, MEAG, and Dalton as well. We have a unique situation here in Georgia where the system is co-owned. It goes way back to 1975, and it provides Georgians with some specific benefits. One, the system is jointly planned and operated, and that gives us the full attention, coordination, and focus of different companies all working on the same goal. It alleviates the needs for duplicate facilities. We share substations, we share facilities, we build off the same lines. And it provides more access to more than 17,000 miles of transmission lines to us Georgia utilities. Okay, this is a picture of the Georgia ITS. It's the lines 46 kV to 500 kV or 46,000 volts to 500 volts that cross our state. That is the backbone that supports the system. It's there to support your local distribution substations and lines that feed your homes. Important thing to realize is we are not an island here in Georgia. We're part of a big interconnected grid that functions together as a single unit. The Eastern Interconnection you see on that picture is the largest, most complicated machine ever in the history of the world. It performs like a sports car, and it's got the capability of an ocean liner or a tanker. It's nimble and large. The generators in the northeast stay in synchronism with the generators in the south, 60 cycles a second, 24 hours a day, 8,760 hours a year. There's no deviation. Now, you might ask, how does that complex system provide such reliability? Does it have amazingly reliable components? Not really. We don't have, our components aren't that reliable. We're not sure what components are going to be in and out, but the system works because of redundancy. I'll give you an example. A common system element we need is a breaker. When there's a fault into a transmission line, we have to open that up and separate it from the system. Well, most breakers, you could say, are maybe 90% of the time they work. You could say 10% of the time your breakers don't work. You could make that into a big issue. But we have two breakers there, right there to operate at the same time. So with two breakers in the redundancy, it's only 1 out of 100 times that first zone of protection doesn't work. But then we've got a second zone of protection that kicks in a fraction of a second later, under 1/10 of a second. And that second zone has two breakers, so our protection goes from 1 in 100 to 1 in 10,000. And then we have a third zone of protection as well, with two breakers that kicks in again under a second later, and that gives us a 1 in a million chance of those breakers failing. Now, is that good enough? Well, it wouldn't be good enough if we had a disaster if they failed. What happens if that scheme fails is we have other breakers that pick up, but we just take out a slightly bigger segment of our system than we want. So you could say, do I want my breakers to be more reliable? 90% doesn't sound good enough. Well, maybe it would be good to do more maintenance or buy and bring them up to 95%. Or maybe they're outside, exposed to the elements and animals. Maybe 90% is good enough, and we'd rather spend our resources in other ways. So a key part of the grid is we get high levels of robustness and reliability by building redundancy into it. Common terms, we deliver watts of power, amps on our lines, volts and frequency. There's a lot of other engineering terms I will try to stay away from, but we have to protect for a lot besides voltage. There's a lot of other considerations. But I'd like to give you a kind of a serious exposure to what we do so you can have a kind of an in-depth feel for it. And I'll talk about two types of studies we do, power flow and stability. Okay, this shows a section of our system, and what happens, we model our system. We have computer models that simulate the system because we can't play with the system. We have to do it with models. And it shows us how lines are loading in one part of the state when we have certain outages. And when I look at this, I can see, well, gee, we're heavily overloaded towards Atlanta and going towards Macon, and the other lines are lightly loaded. Well, right there in the middle is Plant Branch, and that's a coal plant that we're having to retire. And so when you retire the plant, you've got to configure, well, where are the flows from Plant Branch going? And a transmission system is not like a highway. It's not like a pipeline. When power goes on a transmission system, it takes every possible path at the speed of light. So when it leaves a point, it goes every direction, divided by, in relation to the impedance of the path. So when we look at Plant Branch, that shows how the energy is leaving the plant. And also, if we take the absence of Plant Branch in, we get a different set of loadings that are shown in red. And now I see with Plant Branch out, the lines that were loaded before are pretty lightly loaded, and the lines that were unloaded before are heavily loaded. So we have to do a lot of simulations to see how do the lines load up, how does the voltage hold up, as we look across different generation scenarios and different outage scenarios. The next slide shows what happens to the system. I want to show how the whole system connects and how it all interacts together and how we're all dependent on each other's systems, why we can't just worry about Georgia by itself. This shows a day in Miami. Florida had an accident. It was a spring day. They had a lot of lines out for maintenance because they were anticipating light load, so they figured the system didn't need as many elements as usual. And the weather surprised everybody. It was a blistering hot day. So not only did they have a hot day, but one of their workmen in a substation made a major goof up and powered out that substation. Nuclear plants tripped. Florida came back online. They dropped a few loads across the state, bounced back. But the system, when the system has a disturbance, the whole system reacts. So I have this picture for you to just see how the rest of the system reacted when Miami had that problem. And it's going to be in real time, and it shows how the voltages shake, how the angles shake, how the frequency, and a lot of system elements do. So here we are in real time. The system's just fine, and then boom, Miami gets hit. So even though it started in Miami, it's all of us. So we're all in this together. It's a complicated grid. That's why we all work together. So how did we know the system? You know, this was oscillations, and those were good oscillations because they started big and got smaller. But in a system like ours, if it wasn't well designed or well run, those oscillations could grow and get bigger, and then we'd start having generation plants trip off and outages. How do we know to operate our system so that doesn't happen? We do a lot of studies. We do a lot of detailed modeling. We do a lot of computer work. And, you know, we do annual 10-year studies. We look ahead 10 years. We put in loads. We put in different generation. We take out elements. We take out multiple elements. We look at extreme outages. We look at outages of every line in a possible right-of-way. And we make sure our system is strong enough and that we operate it so that it will not go unstable or will not have voltage collapse. We also do interface studies where we look at how much power can we ship across lines to other areas. Whenever a generator wants to interconnect to our system, we do the studies again there, and we've got a host of studies. Now, these studies used to be done voluntarily by the industry. The power providers, the transmission entities banded together and decided to do studies. In 2007, through legislation, FERC took over the responsibility, and these studies that we did became mandatory. So instead of these being voluntary association standards, they are nationally required. And our enforcement of that is done through our local region of CERC. So not only now do we have standards on our studies, we have standards on right-of-way clearance, we have standards on vegetation management, we have standards on how often we do maintenance. These are, you know, I can promise you, very serious standards. There's over 116, and they have many sub-items. We are audited on them. Violating the standards can get you penalties that can run to millions of dollars. This is a very regulated for reliability. I will say my company and the other companies here today, we have our employees, our people participate on NERC committees, on CERC committees, as we work on these standards, as we develop them to protect the grid. A takeaway from this is our grid is very robust. We can meet needs across many different generation levels and outage scenarios. It doesn't have to. The grid is stronger than its weakest link. We have a lot of links. Redundancy allows our system to remain reliable despite having outages. It's critical that we plan for the operational characteristics of the specific generators that we have and the system elements, and that we have to maintain flexibility as people use our system in different ways than they have in the past. One thing to acknowledge, our grid is changing. You know, there are more energy and environmental policies along with energy markets, and they're driving changes in the grid. We're seeing different resource mixes than we did in the past. We're having different resource stacks. We used to know this plant would run 24 hours a day. This plant would come on only during the peak. But nowadays, when the price changes between gas and oil and the spark spread markets and all, we're not sure what's running. It's harder. It's harder to provide that kind of flexibility. We're having to integrate significant amounts of renewables. We're working to bring in solar, nationally, wind, nuclear, biomass, and others. We have more storage and demand resources as we're coming, and again, there's a lot of attention on security concerns. In the past, as I said, we designed the system for local generation. Now again, there's more exchange between the states. We used to have well-defined generation resources. Now we have many different resources with greater variability. So there's a lot more modeling we do today. It's a lot more difficult to model a bunch of small units than one big one. We used to serve a known resource stack. Now we serve markets. We used to have a lot of time to build transmission lines. It took a long time to build the plants in the old days, and we used to could string up line pretty fast. Nowadays, they can build power plants, and it takes us a long time to get a transmission line across. So that's one of the challenges we've made. We used to only worry about reliability and economics. Primarily, that was 99%. It's still a big percent, but also these days we're providing more flexibility from our system, and we're helping to achieve policy objectives. I think the grid will respond to the challenges of the future, but it takes advance notice, commitment, and significant resources on our part. And as we do, we'll take our traditional concern for reliability and economics and balance that against flexibility and other emerging values. Now, Heather, please.
Thank you, Russ. Mr. Chairman and members of the committee, I'm Heather Tilley with Georgia EMC, and I'm just going to conclude our presentation with one final comment, and then representatives from all three of our utility partners that are here would be happy to take your questions today. The three utility partners that are represented here today, and that includes the EMCs, Electric Cities, and Georgia Power, we share a common goal. That goal is to deliver electricity, as John DeAndre said, with safety, reliability, and affordability in mind. It is through the seamless partnership that we have both in operating this grid and in other operations in our day-to-day activities that allows us to meet that goal. Mr. Chairman, with that, our panel would be glad to take a seat at the table if you'd like to answer your questions.
That'd be great. Thank you. Let's see. I don't know how to set it up. Do you know how? Oh, is that it? Okay.
That's it.
Okay, there are some questions. I wanted to ask, I don't normally try to go before members of the committee, but I wanted to ask on the redundancy that you'd spoken about. I mean, from telecommunications, I've had to be involved in with different companies, different customers, preparing redundancy for them and their emergency planning, things like that. I think of telecommunications. I think of redundancy of being lines that come in two totally separate ways, so that if there's a some kind of a natural disaster someplace and knocks out lines between two cities, then you have it going another route going back to a central office. Is that the way redundancy operates in with the grid, or how does that?
Sometimes it's that simple, where you just have two alternate paths for a service. In our cases, we have multiple operating paths because we might have to have a generator out, we might have this line out for a mix. So we have a kind of a mesh, bigger network. So in the heart of it, it would be more than just two paths.
Okay, more than two paths. Okay.
But in some cases, it is just
yeah. Well, I guess what I was, and I appreciate that, but it would be more than two paths. It's not two circuits or two lines going down the same. Okay, that's my question. All right, thank you. And we do have some questions. I don't know who was first. Number 19, Representative Dudgeon.
Thank you, Mr. Chairman. You've brought a subject that I love, so I apologize. I have a couple questions. John knows this, but I'm an electrical engineer, so first I want to say the grid, in my opinion, some people call it the eighth wonder of the world, and I completely agree. I think the average person has no clue at how complicated and amazing a thing that they have power 99.99% of the time, independent of generation. So I just wanted to say that first. A couple questions of curiosity. Do we have a firewall on the interconnecting grid that stops in Mexico or Central America, or do we go all the way down to the tip of South America? Is the whole the Western Hemisphere all connected at some point?
No. The U.S. grid,
Yeah.
am I on or off? Am I on now?
Oh, wait a minute, I think, here.
Push the other one, yeah.
This one here?
Yeah. There you go.
Testing. Testing? Or we can just talk louder?
You need to push the button on the bottom of your mic.
The
maybe.
U.S. grid has 3 components. The western grid is
Yeah.
separate. That goes down into Mexico.
Yeah.
There's a ERCOT grid
Yeah.
that is Texas and part of
Yeah.
Mexico. Our grid extends to the Rocky Mountains and up to Canada.
I understand that, but when you ran your simulation and Miami went down, the ripples went out of our thing all the way up into Canada and
All the
back
way
and
to
down.
Canada,
So
yes.
my point is those grids
That's what
are
we-
interconnected to some extent.
Canada is part of the Eastern Interconnect.
I understand. But we don't go into Mexico or to South America. So
No.
Mexico, there's a firewall there. There's no connectivity. Yeah.
Yeah.
Yeah, okay. The second question, that you see a lot of press about the feds thinking about putting a ton of money in to build the smart grid, into the next generation grid and things of that nature. And I know that the control systems are done a lot better. They're more compatible with each other, and I know there's been a lot of work in the past 20 years to get the reliability to where it is, and we don't have as many rolling blackouts like we did in the 70s and 80s. But what is your opinion about the federal government need to put in a huge project? Do we need like a big infrastructure project to put a ton of money in to do a new grid, or we think we can continue to work with what we got and continue to continuously improve?
Well, we are continually improving the grid,
Yeah.
and we are putting in smart relays, as we would call them, computer-based,
That's right.
programmable controller type based relays. That's a big part of what we're doing. MEAG has done a project, and these are being done at the transmission level. You hear a lot about smart grid at the distribution level, but we're doing that as well. Motor-operated switches that can, close in a line and make these adjustments that Russ was talking about, as opposed to manual switches. So there's a lot we are doing right now to improve the reliability and our ability to maintain the system just on our own.
So you don't see the need for a massive federal program at this point then?
No, I think that's in our...
Okay. Last question, and this came up with the bill that we talked about earlier about my solar bill. Over time, my opinion is you're going to see the model, you point out, it used to be the power was generated local and stayed local, now the whole grid is connected. But you're also going to see more distributed generation as opposed to the big monster power plant. The technology is going to allow, 10 megawatts over here and 100 over here, and a little bit different model. So do you think that the current grid can be made to, over time, nothing changes overnight, but moving in that direction, do you think that the grid can be made to deal with a more distributed generation model?
Yes, I mean, as Russ mentioned
Yeah.
in his presentation, yes. I mean, we have to study it. You have to look at local issues. That can, because it is local generation, that may cause some local changes that you need in the area. But as you mentioned, it would take some time to correct the grid and make sure that it maintains that same level of reliability. John?
Yeah.
President, what I would say is in most cases, maybe not in all, but the distributed generation that I think we would expect coming in the future, as
Yeah.
you described, in most cases would most likely be on the distribution system
Yeah.
versus the transmission.
I understood on the main
But
transmission.
it
Yeah.
wouldn't offer any really different challenges because we have some of the same planning criteria and looking out over time, looking at loading, looking at flows. So would it make it more challenging for us? Absolutely. Is technically it feasible? Absolutely.
Okay. Thank you, Mr. Chairman. I appreciate it.
Thank you. Somebody dropped off and had a question, but we've got 2 to 27. Yes, Representative Frazier.
Thank you. Thank you, Mr. Chairman. I represent Burke County, where we have Plant Vogel. Very excited about our 3 and 4 nuclear reactors coming online in a few years. My question is, when we were looking at the simulation and the question was made, is it a technician or somebody made a little light boo-boo, and that happened. I was looking at how the simulation went. What is the time frame for that happening, and I know that was the grid, but getting back online, was that like a matter of seconds or a minute for that whole region to go out and then Georgia Power or somebody kick back in and it comes back on? Because sometimes when we're at home, we get that little click, but we don't know what just happened. I don't know whether it's a grid or was it Georgia Power, having a problem.
Nobody in Georgia saw, all of that went below your radar. Nobody in Georgia saw a light dim or anything.
Okay.
Only people in Florida, what you saw happened in real time. He touched something, And that was happening in a second. All of a sudden, nuclear plants tripped off, and what Florida did was they had a shortage of generation because they tripped off the nuclear plants because of what he did. And so they, at like 8 different locations in Florida, tripped load to balance it. And so some of that load that was tripped across the state was out anywhere from 15 minutes to an hour. And then after that, everybody in Florida was fine. So we were never touched. Florida was probably 3% of the state's load out for anywhere from 45 minutes to an hour because of a grid accident.
So a lot of times when we're having these, we don't even have any effects from them. They may be happening in another area, and we just don't even know it. Mm-hmm. Right.
Representative, sometimes if you're at your house and your lights flicker or go out for 2 seconds and then come right back on, that could very well be out on the distribution system where something, let's just say a limb fell across.
Okay.
We've got controls and protections schemes out there to allow that fault, i.e. that limb to clear. So what it does, it may automatically drop the line. You go in the dark for a couple of seconds. The fault clears, and then the power comes back on. So some of the automation and other things that we've talked about, even though you may be out for a short few seconds, that's the system, quite frankly, operating as it's designed. Mm-hmm. If it didn't do that, and the fault never cleared, you got other problems,
I'll be calling.
Extended out.
Yeah, I'll be calling Georgia Power because I want that deducted from mine.
Absolutely.
Thank you.
Representative Smith.
Thank you, Mr. Chairman. I'd like to thank all 3 of the panelists for taking the time to come and kind of deconstruct this big piece that many folk really and truly don't understand. Fortunately, nerds rule on a day like today. I feel comfortable here. I'm a former major in the U.S. Air Force and communications commander, and so much of this is right at home. And I think that one of the things that I found interesting is that when you spoke of the grid and the sensitivities, much of this is not policed by humans. Much of these sensitivities are beyond our comprehension, that these are computer-generated sensitivities that would really and truly be affected in a much better way on a positive side, especially with redundancies that you spoke of. How can we get some assurances from you that with these redundancies and with the sensitivities, and I know technology is an ever-changing process on the positive side, are there any cutting-edge componencies or intricacies that you can share with us today that we probably don't know about, that may be on the cutting edge of where you're going, that you're able to discuss? Something that won't put you out there and where you have to expend some money and say, well, we committed it, so now we got to do it.
Can I take you back a couple years from cutting edge? I will tell you one problem we have with the Atlanta area is you can't build generation in the Atlanta area. And so the generation comes from further away. And one of those things that I said I wasn't going to say was VARs. VARs are a lot like watts, except watts is where, kilowatts and megawatts, that's where it does the work in your house and the factories. VARs are like watts, but they don't do any work in that sense, but they do support your system and your voltages. And without generators, an area has a VAR shortage, and it's hard to get VARs there. And so Atlanta, we discovered a few years back, was at risk of going in the dark when all these air conditioners are running, because if you get a fault on peak, they sucked all the VARs. So what we do have is we have a $24 million device that it combines power electronics, just like your electronics in your computer, but instead of this sending dots to your computer screen, this sends massive amounts of capacitive power to the grid with fine computer controls, power electronics, and capacitors, and it protects Atlanta. We've got this device. We expect it might only will only be needed once every 50 years, but if we need it, it would be seriously needed. This device is in Winder, and it's protecting Atlanta from a voltage collapse.
Thank you. I wanted to ask, now, there are obviously, I shouldn't say obviously, I don't know if it is or not. When you have these transmission lines, there must be long distances of them that, where there's no population really, they're just going down through the country. and I get, and I'm assuming that that's where the smart grid, or having some kind of something at certain intervals along those transmission lines that could give you information about what's happening, about the load, whether something is broken or anything like that. What is the status with our transmission lines in Georgia? I think that there was stimulus money that came down through GFA a few years ago. That it was my understanding anyway that some of that was used to do things like that, to provide some of that smart technology. I mean, am I wrong on that, or is that true?
Well, in the case of MEAG, we did have some Department of Energy monies that supported our smart grid work on the transmission system. I'm not aware of any.
The same with Georgia Power. I think from stimulus dollars, what we have done is automated, if you will, with smart devices, both on transmission and distribution. Is it all we'd like? No, but we've used that money mainly to further automate our system, Mr. Chairman, where we can, as I say, automatically, but without human intervention, if you will, react to situations in a remote area or where it would not take us putting someone in a truck to ride out to look at it. So
right.
That's where we've spent what stimulus dollars we've had, and I think probably all three of us have done a lot of that.
Yeah. Well, I'm not trying to put you on the spot at all. Really, here again, I appreciate y'all coming and just trying to get an idea of the status and what it is and what it does and things like that. But I guess going back to a previous question by another member of the committee, as far as that, I don't know what you would call it, the smart technology or whatever, in our state, what you all touch with your companies, and what is the progress? I mean, are we like 20% of where we need to be? Are we 10%? I mean, where are we in that? How much further would we have to go to get where you all think that we should be?
I mean, to put a percentage on it would be difficult, Mr. Chairman. I think we have, and I'll speak to Georgia Power and let these gentlemen speak for their companies. I believe what we've done is taken the technology that's available, and Smith said it's ever changing, and we've tried to integrate those components into our system where it made both good operational and economic sense. It's a never-ending, quite frankly, a never-ending proposition as our system grows, as we get distributed generation on the system. It changes some of the planning criteria, and there are other components and things that we need to do. So I'm not trying to steer away from your question. I think it's just difficult. I think your system becomes more sophisticated as the need for it to, and we continually look 10 years out trying to model both transmission and on the distribution side to take into account those things that we believe are coming, both from a technology standpoint and a load standpoint.
Right. Well, I have a couple other questions, but we do have questions from members. Is that you, Representative Dudgeon?
Yeah, I just have a quick follow-up.
Okay.
Yes, just a quick follow-up on that. It sort of goes to the smart grid question. How many humans are left in the loop? I saw what happened with the Miami event. Obviously was not human involved. No one could react that fastly. So if no one showed up to work on the grid tomorrow and no one's there and it's all just the machines running, are there any humans left making decisions, or only when the machines would fail, the humans have to step in? So how many humans are still in the loop, I guess is my question.
Humans are critical.
Okay.
Every organization has control centers. This is being monitored. Some of the things have to be done very quickly, but some things are judgment calls. They're watching things develop. There is human intelligence involved.
That's what I figured. Go ahead, John.
We all have control systems.
Yeah.
Control centers at a generation, transmission, and distribution level that are obviously humanly manned. I think the smart grid technology, whether you're talking about it, Representative Dudgeon, a distribution or transmission system, really all that's afforded us is an opportunity to react, understand, and clear up the situation much quicker than, say, 20 years ago.
That's right.
Where you had lights go out, you recognized it was a fault on a particular line, but you had to actually send somebody out there to
I understand.
find out what it was.
Yeah.
Technology's allowed us to more quickly determine what our issue is, so we can take some human intervention and clear it up.
Well, that's my point. Your Miami event showed that a lot of things can be handled automatically because a human didn't intervene in that situation. But I know y'all make macro decisions about things in order to optimize the situation.
And
But
as I commented,
yeah.
the system took those loads off in
Yeah.
Florida,
Yeah.
but human beings made sure it was safe before we put them back on.
I understand that, but the grid kept the country up on its
Yeah,
own.
yeah,
That's my point, is without a human having to step in, the smartness of the current grid was able to keep the country from going down with the waves and the oscillations and dampening them down. Yeah. Thank you.
And I would comment, I mean, I'm an engineer, and I like to keep busy, and I love to do interesting things, and I would love money and have a grid out of science fiction. But I have to honestly say, I think our grid is in excellent shape. I think we provide excellent reliability for cost. I would not classify us as being behind in any way.
Okay. I mean, that's great. Representative Dickey has a question.
Thank you, Mr. Chairman. I wanted you to expand a little bit on these FERC's security rules, and Chairman alluded to it a little bit in his opening remarks about we saw this summer in NCSL. Some people in other parts of the country is extremely concerned about security. I worry about cost and the extent of where do you go with these security things, and I assume y'all are looking at those.
We are, absolutely, and as we mentioned before, we view physical security in a similar manner as we do other events that may damage the grid. And and redundancy of the system is really the key to ensuring that you have good reliability and can recover from those. So, you know, our focus has been on this redundant system, and it will remain to be that. We think that's the best focus for these physical security type issues.
I would also say that we take steps, at generation plants as an example, where we have physical security there, but probably equally, if not more important, either at the plant or on the lines, is what you do and how you react to those situations when they do happen. Because the situation that happened in California recently, where a transformer was shot up, unless we physically had, I don't know how you would protect that asset to keep some crazy from doing that. But the important thing is the redundancy and then the physical or human reaction of your preparedness plans to go take care of those kinds of situations. And that's part of what this FERC order does, both from physical security and water preparedness plans.
Thank you.
All right, thank you. I want to ask you, out of that meeting with the NCSL last year, maybe I was in a lot of different meetings, and maybe I misunderstood this, but it seemed to me like they brought up something about, I think the language they used was not a matter of if, but when it's going to happen, something related to sunstorms or something to do with what. Tell us about that, because I mean, unless I know more about it, that's really scary to me.
Well, the sun erupts, and you can study transmission lines will pick up an induced current from solar flares. One thing we know, we in Georgia, the closer you are to the North Pole, the more of a risk that is. And it has to do with your lines running, there's a difference between north-south lines and east-west lines. So we in Georgia, whatever the risk is for solar flares, we're south of Kentucky where it's greatly diminished. Now, there are some things you can do if you know it's coming, and you take your transformers out of service, they're not going to be harmed. If it's in service, some of that ground current will go through and maybe overload and burn up your transformer. There are certain steps you can take to protect your transformers where it redirects ground current, but there are, it's like any kind of risk protection. You protect one kind of risk, and you might subject yourself to somewhere else. As people look at solar flares, I mean, I've heard a lot of different opinions of it. I think lately the trend overall is going down as far as the fear of it, but there are some people that are convinced it's the worst thing in the world.
I mean, is this something that happens or has happened, or just something that the fear will happen?
I believe the last solar flare, there was one that took out some facility in New Jersey for a little bit.
Okay.
It wasn't the whole grid. Some transformer somewhere picked it.
But hence that while we build redundancy into the system, because if it's that situation or some other type of
Okay.
situation that were to take that transformer out, then we've got redundancy to pick that up.
And I
Okay.
don't want to be over casual and not take, because we take every threat seriously.
Right.
We're still looking at the evidence as it comes in. But you could say, gee, if we'd have spent, $500 million in remediation, we wouldn't have lost that $2 million transfer.
Right. Okay. Thank you. Representative Dudgeon has another question.
Well, you activated my nerd gene with this topic, Mr. Chairman. I apologize. I know NASA's put a solar observatory just for the purpose of forecasting the solar weather, because if you get a few minutes notice, like you said, I mean, they do take it seriously. It's a big enough solar event, no matter what we did as humans, a big enough solar event will take it down. But the question is that something happens once every 10,000 years, once every million years, kind of like an asteroid. But it is a real situation where, and that's why, one reason I have that solar observatories out there is to forecast the solar weather so that we can tell our friends in the grid, by the way, you need to turn off New York because here it comes.
Thank you. Chairman Geisinger has a question.
Since you are tied in with everybody from South Florida to Canada and have been for years, let's assume that there are 3 high-level bursts, atomic bursts, and they blow out the transmission lines in regards to the interconnections. The systems can fall down and be localized, can't they?
Yes. I mean, we do, one of the things we do at the grid is you monitor your ties, and when, you have the smart computer controls. It's like guys climbing up the mountain in where they're all strapped together. If the fellows next to you you're falling and the group can hold them, you're going to hold them. But if there's a risk that they're going to pull us down, we let them go. And so the system would let go.
Because most people get a little bit nervous about that.
Yeah. So if there's serious problems in Canada, we go on our own. I haven't reviewed it lately. I'm going rough on my memory, but when they had the New York blackout, those areas started going. I think we cut our ties. We said, you went where you shouldn't have been. Sorry, we're on our own.
Thank you.
Thank you. I appreciate you all coming. I know it's, I had questions about it, and obviously some other people did too. And, as I said this morning when I went to the well for the morning order, I just know it's something that is, it's extremely important. I know it's something that, here in Georgia we're interconnected. It's not just here in Georgia. It's something we're interconnected to across the country, and in some cases internationally. And, and I know it's a matter of, when our lights go out for a couple hours, it's an aggravation. When the power was lost, during the storms for people for a long period of time, it's more than an aggravation. I mean, it's a real problem. But if something were to happen to the grid, and I'm just saying this as a non person who's not involved in the energy industry or anything, but I see it as something that could be, catastrophic. Really, if something possible, and that's what I was trying to get at. What are the possibilities of those things? I know that during those storms, I think one of the local meteorologists said that the storm that was coming was going to be of biblical proportions. Well, it really wasn't. I mean, it was bad, biblical, but something going out with a power grid where it could actually affect a large part of the United States or whatever for a large period of time, that would be, in my opinion, biblical proportions. So that's why I thought it was important enough to get us together and ask you all to come. But it sounds like to kind of come to a conclusion that it sounds like we must be in pretty good shape. That y'all are doing things to modernize and improve as needed, and as it's not too expensive and will break the bank. And I mean, that's pretty much what I'm hearing. I believe. Okay. We're going to have to get out of here pretty soon. I know we had the room for an hour, but I see a bunch of people standing outside. But, Coach, you have a question.
Thank you, Mr. Chairman. No, I just woke up from a nap. But
okay, well, I thought maybe that's what it was, too.
No, is there somebody building a big boat somewhere? You see it? Big biblical coming?
I hope. I hope that if there's something coming that somebody is building the boat, yeah. Thank you for your question.
You're welcome.
Thank you for your interest. All right, thank you. Any other questions from members of the committee? Thank you all for coming. I appreciate the presentation very, very much. Thank you. With that, we conclude.